I could grab one.
I just need a staple. Audrey. Should have. Well, you can always try next year.
I don't think so.
You don't think you can?
Well, like the transfer one is for
Oh.
going into.
I think they have a graduate one, don't they?
Yeah, but that would be a master's program. Right?
Do it, yeah, get it.
Yeah,
Try, you can always
a
try.
master's program.
You can always try.
I'm not gonna do a master's program.
Yeah. Yeah, I don't know if I want to do something like that. I mean, if I had the opportunity to do it, like, but my goal is just getting the bachelor's, right? It's simple, yeah.
I wanted to get my doctorate, and I might still, but I'm a little overwhelmed.
Well, that's very far in the future, so thinking about that sort of stuff right now is like.
Oops. Oh no.
How's that? How's that?
I don't know what to say when I'm on. You're fine. You stay.
All right, happy Tuesday. So before we dive into lecture, we have a lot of announcements. And so let's just talk about the midterm really quickly. So I was actually overall pretty pleased with the scores on the midterm. And so I don't want anyone to worry because there's probably going to be some normalization at the end like there usually is, but there was a pretty good distribution of the scores evenly, so I was pretty pleased about that. So I'm probably not offering any corrections or anything. I don't think it's necessary. And so again, I'll hand those back today. The grade should be in your grade book, and then we'll just look towards the final. You guys have made it right the whole year of Gen Chem, so I'm not looking to fail anybody. That being said, right, complete your labs and everything so that I can, just normalize the grades and then people will fall in nicely like I think that they will. Again, just based off of the distribution. All right, so just complete assignments. And so somebody already told me that I was missing their homework today. So double check that. I'm going to hand back today during lecture everything that I have graded, which I should have caught up. So everything should be up to date. So just double check that everything looks good. And let's see. Oh, other things we should talk about. So it will be here before we know it. So let's just look at our syllabus. So we're doing our radioactivity lab and then jump all the way to week 10. And that's our poster presentation for our paper. And if you've poked around Blackboard, you notice that I put up a poster example. And so you can go through this. So there's two different posters on there. And now this is going to take a while. So one is an old poster that I presented at an ACS conference. And so you can use this as a template, change all this to RCC, blah, blah, blah. But this kind of gives you an outline of, how to structure a paper. You don't have to do it, with these text boxes. You can rearrange them. Some people do more on the side, like a trifold. And so that's the other thing that we should talk about, because unfortunately you're on your own for the poster. I was trying to convince marketing to do it for us, but I guess they weren't up to it. So poster presentation, so I'm going to be pretty lenient on like the format, right? Because I don't expect y'all to go get it professionally printed. I think the cheapest option is Staples, and I want to say they start at $30, but that could be old information. So I don't know what the going rate is, but that's kind of expensive. What you can do is I think you can take this and print it out as like a slideshow. Of course, I would have to play with this and see. So I think if you like print it as a slideshow, it should kind of print all the panes and then you have to like paste it together, which isn't the worst thing in the world. Or, you could kind of cut and paste, kind of, whatever model of poster presentation kind of works. And then you can also look at, so I have another reference on there. So this is actually, if you know Kevin Murphy from math, this is one of his computational chemistry posters. So Kevin is actually a computational chemist by training. And so this is just, again, a different structure of a poster presentation, kind of give you some inspiration. Unfortunately, his is in a PDF format, so you can't edit it, but you can kind of see, again, how to incorporate text and pictures in a presentation format. And so, right, you could do any sort of poster presentation format, right, either poster board, which I think they still sell at the dollar store, same with a trifold. I don't have a preference, more of a style. My preference would be you practice printing, but again, that's like expensive, so I don't expect people to do that. But that's just nice, standard. And so you just want to translate your paper to a poster. And then I've been kind of giving people feedback, but I think I've missed people. So if you still need paper feedback, just email me your paper again or your updated copy, like, ASAP, so then I can give it back to you. So just email me your new copy. And I know some people didn't turn in a draft last quarter, and if you didn't, right, just give me a current draft so I can help you. Or again, I think I've missed a few people, so just ping me a new copy so I can print it, because I need a physical copy. That helps me. All right. Oh.
How big are you wanting the posters to be roughly?
Well, that's kind of the, let me look at Staples, because it's just like a standard poster board. Yeah, usually that's a standard. I was trying to look at the Staples website. Yeah, because if you go to posters, and where's, because a good size is either the 24 by 36 or 36 by 48. So that's 2 feet by 3 feet. It says $37.50 for 24 by 36. So that's probably the smallest standard size. That's probably, I assume, what the poster boards are roughly. So that's a good size if you're just buying a poster board. So yeah, if you want to go through Staples and print it, it's $37.50. So I'm off for my prices, inflation. They never go down, those prices. But yeah, from what I remember, Staples is the cheapest, because there's also Kinko's, but back when I looked, they were more expensive. But you're welcome to search around, obviously. But again, if you don't want to spend money, right, it's just fine to do a poster board, print it out, and I can help you with that, right? We have color printers in the science department, so we could do that, ourselves. No, we don't have time with that. I mean, I hope you're okay with that. But yeah, between the poster presentations and everything else, I mean, we could get rid of the poster presentation and do a horrible lab practicum if you'd rather do that, graded on accuracy. Let's see. Oh, that being said, for the poster presentation, because it's on the syllabus, it'd be nice to do it on lab in Tuesday of that last week. Does that work with everybody's schedule? So if we would just not have the Thursday lab, and then we'll just all meet on Tuesday. And so like I had promised, right, we'll do it like an actual little conference poster presentation, have some refreshments, some snacks. and then y'all can share your science and, be a fun week 10 activity. Unless instead, you want to do the lab practicum, and I can make a torturous one.
I'd rather talk about mushrooms.
Yeah, unfortunately, no mushroom samples there. All right, so yeah, put that on the calendar though for week 10. So we'll all meet in the Tuesday lab, have our poster presentations. And then if there's, one person who absolutely can't, you can always like do a video recording of your presentation, but it'd be a lot better if you can, of course, join the fun. And then so last other event and distraction from school is, so don't forget we have World Day that is coming up next week actually, so really fast. And so we have to talk about ice cream so we can participate. So World Day, it takes place during our class, and it's only on the Riverside campus. And it is from, I think, 11 to 2 p.m., so right during our class. So instead, I had said we would make ice cream and share our cultural ice cream. And so I was going to pass around ice cream group sign-ups. And let me just throw up, so a basic ice cream recipe. And so the good thing about liquid nitrogen is you can really kind of stretch it and do different permutations. Like it's pretty good with vegan ice cream, which is surprising. Like I've made ice cream with just oat milk and it was okay. But a basic good ice cream recipe is 2 cups of milk, and usually I use whole milk because I like it to be rich. 1 cup heavy whipping cream, and 1 cup sugar, and then usually you add in just like some vanilla. And then so kind of your job is how to change this. So again, if you want to do like vegan or alternative milk, that's a cool thing. You could, go easy, just add like chocolate to it or different, I would do like marshmallows, campfire, whatever. So kind of think about cool, creative permutations of this recipe. And then I would say we want to get in groups of probably around 4 people. So if we have some groups of 3, some groups of 5, that's okay. But probably 4 people, that'll give us like at least 5 or 6 groups, I think, with our class. And that's a lot of ice cream making to share. So I'll kind of pass this around. If you need some more time, that's fine. And then I would put on there, so your group members, and then like tentative flavor. Just because I don't want everybody picking, the same flavor of all pick chocolate. You can do mint, you can do plenty of things. If you need recipe ideas, I have plenty of ice cream ideas. All right, any other announcements? Coffee, ice cream, throwing out all good ideas. All right. All right, are we ready to do radioactivity, or are we too excited about ice cream now?
When are our papers due for
Oh.
the field trip?
Oh, the paper is due for the field trip. I mean, we'll just say by the end of the term, so no one's stressing, but yeah, probably like week 10, don't wait till week 11. Other questions? All right, so let's dive into radioactivity then. And so kind of, right, well, we're at the end of our chemistry journey in a lot of ways, right? We only have 4 full weeks of lecture and barely at that. And so now we're kind of getting to the hodgepodge chapters, at least that's how I feel about the end. And so this last bit is a little bit of a recap, right? Because we mentioned at least radioactivity briefly when we talked about reaction rate. So we're going to kind of go over that again. It'll probably look, the same. So a little bit of a refresher, but then we'll add in a few new elements, which I think the physics people are going over because I saw your test a little. We'll see, maybe it was just conversions. And so if we recall, right, radioactivity is just defined as the release of high energy particles or high energy electromagnetic radiation from the nucleus of an atom. And so of course, right, we can define anything that ejects particles as being radioactive. And I think I've shown you the chart of the nuclides before. And so again, if you get really bored, you can look at that online or in lab and look at all the radioactive species. And so we mentioned that these radioactive nuclei, they decompose into smaller nuclei in a process referred to as radioactive decay. And so, right, these nuclei are unstable, and so they emit these different particles. And so our parent nuclide is the nucleus that is undergoing radioactive decay, so that's referred to as our parent isotope. And then the daughter is the resulting new nucleus, so the main isotope, so the higher number. And so anything with 84 or more protons tend to be radioactive. And so this, again, is a recap so we can recall that we went over these three types of decay. And so alpha, so what was alpha particle? So it says it has a charge of 2 and a mass of 4. So what does that correspond to for alpha particle decay? Helium. And so we'll write our atomic symbol. So that's always right, our hint. Oh, I know that's alpha decay. I have my alpha particle. And if you recall, right, we said that this was kind of the heaviest but also easiest to stop. And so that's what you'll be doing in lab today, is figuring out like which ones can penetrate different materials and comparing your radioactive counts. And then we mentioned beta decay, and we also mentioned that this beta decay, this one is focusing on negative beta decay, but there's also positive beta decay, which we can, again, remind ourselves. And so this has a negligible mass, so we can also kind of think of this as, right, electron-like, and so same thing, beta positive would be positron-like decay. And then our gamma radiation, if you recall, so this is just light energy, so not a particle, so there's no particle emitted. And blah, 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 so this is reminding us of the positron emission, aka beta positive decay, so just depending on what source you're reading, how it refers to it. And the other process, I don't remember if we mentioned it last time, but sometimes you have this process called electron capture. And so just like it sounds, a low energy electron is pulled into the nucleus. All right, so let's look at those in more detail. So again, just kind of going over it. And to recall, we had said before, right, we balance our nuclear equations by adding up all the top numbers, right? So the top numbers have to balance, so the total mass, and the bottom numbers have to balance on both sides. And so with this one, we have uranium-238. We could say, right, this is alpha decay, and then we could have figured out the product 238 thorium by just subtracting 238 minus 4 and 92 minus 2. So that gives us our 234 thorium. So they have those labeled as our parent and our daughter. And so like it says here, it is the most ionizing but least penetrating. So again, you'll get a taste of that in lab. And so it should be stopped by paper or a cloth. And then again, because it's a helium, your number decreases by 2 and mass number decreases by 4. look at another. So let's do a quick predict a product here. So what if we have 222 radon, and it undergoes alpha decay. So what's the daughter isotope? We'll do another one too. So you can also try 172 gold, and it also, oops, does alpha decay. RN here. All right, what do we get for the products of this radon decay?
Got a polonium, which is atomic number 84, and the isotope number is 218.
So I like it, and just double check, right? 4 plus 218, 222, 2 plus 84, 86. And of course, 84 matches with polonium. Questions on this one? And then what about this gold decay? What do we get for the product? So 168. Questions on that one? All right, so then we'll continue with kind of our refresher recap. So then we said we had beta decay, and this is our electron-like particle. And I would go ahead and write our symbol, so that helps us, right? So it's a massless particle. And then this -1 is also a bookkeeping mechanism to help us. So notice, right, an electron plus a proton gives you back a neutron, since our beta decay is, again, massless. So that kind of makes sense. And so, again, this is referring to our negative beta decay. And so it's emitting our electron-like particle. And so they're 10 times more penetrating than an alpha particle, but only half the ionizing ability. So again, we'll play with that in lab. And so this beta decay is actually what's responsible for radioactive dating. And so I think we had mentioned it with our rate chapter, but this is essential for dating things. So 500 to about 50,000 years old. And so, right, I'm sure that's what they use on the caves. So they mention, right, the fossils that they found and dating them. They also mention, right, dating the columns, and all that is done with radioactive dating, and then just comparing the ratio of your parent nuclide versus how much carbon-13 and 12 you have. And so we can write out this reaction. This is kind of a classic example of our beta decay. Oops, sorry, -1 beta. And so mathematically, again, your number doesn't change, your mass number, so still 14, but then we're at 7. So by losing our electron, right, it gets converted our neutron becomes a proton, essentially. So, right, we can see that with our splitting. So neutron splits and our carbon, mass stays the same, loses our electron. And so other examples, so phosphorus can also undergo beta decay. So what would be the product of this? Excellent. So we make sulfur 32 for our product. And so then for our gamma, usually they have to tell us that it's some sort of high energy metastable state. And so this gamma radiation, notice, right, it has no mass, no atomic number, so it's just 0, 0 with our little Y symbol, or gamma. And so they're high energy photons, and no change in the composition. And so usually it has some sort of M to say that it's metastable, and then of course it decomposes right to that same isotope. And so they're the least ionizing but have the most penetration, and so the protection would be like lead plates or cement walls. And so this generally happens after there's some other type of decay, and then the remaining particles rearrange, so some sort of process. And so then our last one is our positron emission, otherwise known as beta positive, and that's kind of more obvious by its symbol. And so now it has a +1 here, and symbolized by a little electron. You might see beta positive, potentially, again in another textbook or reference. But again, main thing is it's more an anti-electron. And so mass of the electron, but opposite charge. And so a positron is formed from the nucleus when a proton transmutes to a neutron. So, right, a proton splits, we have a neutron, and then our positron is emitted. And so this is our kind of classic example of a positron emission. So our phosphorus, now 30 isotope, decomposes to silicon 30 in our positron. And then the last one we mentioned was the electron capture. And now we have a proton plus an electron combining to make a neutron. And so our mass number would stay the same, and then our atomic number decreases by 1. And so this is just the same reference. If you need another chart, I can print one out. And again, it goes through the kind of the classic reactions. Don't forget this technetium one that we saw last time where it has that M, again telling us that it's metastable so that we know it undergoes the gamma. And then we can look back at the other kind of reference for our positron capture with the ruthenium. All right, so then blah, 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 we went over this. And so let's look at a little, we're going to take this a little bit deeper. Right, so we went over this roughly last time, just saying, okay, well, right, we sum the top numbers, they have to match, and then the bottom numbers have to match. But now let's kind of dive into this deeper. So now we have what's known as our mass defect. And so does anybody know what this is referring to? And so let's look at this. And so it's defined as the difference in mass between the nucleus of an atom and the sum of our separated nucleons. And so this is kind of getting at, well, where does the energy come in from these nuclear reactions, right? And we can recall we have E equals mc squared. And so now let me give you some numbers so we can actually see what we mean by this. And so our example is if we take bismuth, we're looking at isotope 209, and you have to, of course, use the precise mass. And so its true mass is 208.9804 atomic mass units. And okay, so if we want to find our mass defect, then we have to add up everything. So basically, let's take its components. So it has 83 protons, and you're given that the mass of a proton is 1.007825 atomic mass units. And again, if it's isotope 209, then it has 126 neutrons. And our neutrons have a mass of 1.008665 atomic mass units. And so now let's go through this math together. Let me pull up my calculator. And okay, we're given this mass, so let's compare. So 83 times 1.007825 plus 126 times 1.008665. And so, oh, there, that looks interesting already. And so we have a mass of 210.74, 741265. And okay, so this is where, right, we have some energy stored here in this mass defect phenomenon. And so let's take that difference. So now our difference in our masses here. And so when we added them, so we got that number, 1265 minus, so our 208.9804. And so we have this difference of 1.760865 AMU. And so we need to get our energy units straight. So we'll go back to E equals mc squared, but we want to calculate this in mega electron volts. So our C squared is equal to 931.5 mega electron volts. So that's just what the nuclear binding energy is usually in, so electron volts. And so now we can plug our AMU in. So now we're in the right units. Oops. Throw my pen on the ground. And so now we can just multiply these two together. So times our C squared in mega electron volts. And so now we have, right, a total of 16,000, right, 40, I'll round it to 0.25. So 1640.25 mega electron volts. And then that's spread over 209 nucleons, right? So I'm just taking protons plus neutrons. That's 209, aka how many things are in there. So this is just our average. And so now we're kind of saying, well, each, nucleon is worth about 7.848 mega electron volts. So now we're kind of seeing where that energy comes from in our radioactive equations. So that's kind of cool. And then this is just a reminder. So this might come up again. So remember, this equation is useful for half-life problems, or we might just see kind of the more basic half-life problems where it goes through. So instead of depending on the equation, it just kind of asks like how much of the daughter is present after so many half-lives. And of course you can go through and make your cheat sheet. So 0, let's just start off. We have 100% of the parent, and that's at 0 half-lives. And then of course right after 1 half-life you have 50% of the parent, and you can add, right, 50% daughter if that helps you. So 1 half-life, and then just continue, right, having, so 2 half-lives, so 25, 12.5, 3, 6.254, and what is it, 3.125? Is that right? And so usually we don't go past 5, but you can keep going to 6. Or again, you have the equation, but just kind of your basic half-life problem. All right, now's probably a good time for a break. A little early, but we're going to shift to CHEM, so we might as well reset our brains anyways. So I'll continue handing back papers, and then make sure the ice cream sign-up is still going around. And if you have questions about that, I can help. And let's try to meet back in like 10 minutes. So. Did you get some sun this weekend? What do you do?
I ride horses for work. So
Oh,
I
that's
just
awesome.
stayed at my TikTok and I was like, I'll get a tan. Yeah. She's never gonna get it. She's never gonna get it. I don't know. I heard it. bad. I'm just like, the hardest one I felt like I've ever done. PH series. There were like, I don't know, maybe like four that I would the rest of them I was like,
Yeah, you were at the con.
people remember my last name. People remember my last name way more like, yeah.
I was like, why would I? And I was like, wait.
She spelled my name.
Yeah. I see how it is.
You spelled my last name.
Yeah, because you talked about how you would get.
Oh, yeah.
That's
Guess
interesting.
what the context of the jokes were.
Oh, it's okay. Oh, wait,
So is that final decision? No one else?
oh, do you want it? I like coffee.
On the back of your laptop, you like have to go to this website, look at it, find the article and answer from journal. The first, I think I put it out.
Wake me up. Me?
How dare I have a bladder? Yeah, the black.
It's crazy in there. Do you have any ideas for flavors?
And there were like two. So I did call her and welcome her, like, how do I even do this? And she's like, I don't know, actually. I can't help you. I'm like, fine. So I just turned them in and they were only half done. I don't really sure how somebody turned Yeah, this one. I know. First term I was really good. I turned in my lab and my homework every week, a week or more. And second term I did for like half the term. And then I had done maybe turned in like one homework. But other than that, no. That was the hardest test I've ever done in your classroom.
Oh, yeah.
That test was difficult.
Although, I mean, I feel like it's just the content too.
Yeah. Yeah, fun.
Doesn't matter.
Yeah, I'm not even saying like the test, it's just the content, like I did not understand any of that stuff.
It says to mix in oil with it, like something neutral.
Yeah, so the stuff you see online, the after nitrogen, like I said, it's more forgiving because it's a lot faster. So you don't have the same
It was like a
problems.
green
So
light
it's
right
colder
now.
here, right? So the problem is trying to thicken it out. Now you're using like a freezer. Yeah, because I've made oat milk ice cream from literally just oat milk. Although I usually recommend like using like coconut milk or thicker stuff.
If we add to it,
Wait, I like it when we add like
Soy, I mean, like I said, liquid nitrogen will be more forgiving, but you just want something like thicker, so that's why I recommend like the coconut milk in the can that's like super thick, like the Thai coconut milk. Like that's good. But yeah, otherwise, I mean, just like you probably force this one to work, but I think that's not.
you just buy a bag. Yeah. I'll do that. They're not there. Do you think we're gonna water? No.
I got one.
We just like melt down
Yeah,
some
one
sugar
for myself.
into like a little sauce, and then you just like kind of pour it in, like fold it into the thing so there's like little stripes.
Oh.
Yeah, I was thinking what too, it's like they made little like cake pieces. Yeah.
I like your ice cream ideas. I was listening in.
Thanks, you're not probably
It's just one test. I also go for chemistry career. He's getting degrees.
Is this on a 107?
Yeah.
Oh, that's why. I was thinking this is different than what Blackboard is.
Yeah, I didn't tally it up properly because I threw in a question at the end, so that's why it came out to 107. But yeah, your percentage is correct, yeah.
It was with the yellow paper. We had to spell it out. No, it's just a lot of people only have to.
No, a lot of people do just like drop, like they don't even show up for the midterm and then just like disappear.
See, like with my biology series, people only had to take like the first biology
Oh,
course, like all the
weird.
nurses only had to take the first term of it.
Oh.
So we had like a significant dropout. So I was thinking that's the same thing with chemistry. No, I can do this good.
Chemistry's hard.
I agree.
And it just like self-selects too. I didn't even get a chance to fail anybody.
My mom is a chemistry.
Oh, nice.
She's got like a master's in chemistry and all this stuff, and I cannot do that. Cannot. I'm a biology person, and she's not a biology person.
Oh, that's funny.
Yeah.
All right. Did everybody make it back from break? Give people another minute. Yeah, Carmen's still. Yeah, there's also.
There was like a little like spinny one, but it's like this big. Yeah. Everyone's got. You don't have to. Actually, good morning. I'm thinking that when I go back to my I just don't want to like put my name on it. I did the only thing, I think it'd be easier there, and that's the only thing I'm worried about. I was focusing up in, I mean, it's really not there, it's just here, but like if you come Yeah, my friends makes no carbon. See this?
I like that.
It's huge. I need a, what is it called, like a, yeah.
All right, let's shift gears to OCHEM. Well, we'll save that for lab time. Then you can come up with more ice cream. Yeah. All right. So, does anybody know what an alkane is? Do you remember? I think a Lero. Oh, no. So it is a hydrocarbon, yeah. So alkanes could have halogens, but we're just, it's even more basic. But what else about alkanes here? Oh, no double bonds. So the alkanes actually means so no double or triple bonds. So these are just our basic alkanes, and so hydrocarbon implying that they're just mainly made up of carbon and hydrogen, and we will look at some substituted ones.
Is there an OH group?
There could be, so that would be like an alcohol. So we'll go into functional groups later. So OH, right, those would be for substituted alkanes. So we'll get into our alcohol groups. So hydrocarbons, and then so alkanes, the alkanes also means that they are fully saturated. And so fully saturated would be like our saturated fats. That's what I should have gotten. Hang on, I'll have to pull up a picture of saturated fats later. And so let's just look at our acyclic alkanes first. And so acyclic would mean, right, not in a circle. So straight chain. So it could also be branched. And so all of these acyclic alkanes have this formula, so CN, and then you multiply that N times 2 plus 2 gives you your number of hydrogens. So for example, we can take, let's just talk about hexanes. So if we have hexane, and we're jumping a little bit into the naming, but hex, so how many do you think that is? 6. So 6, so that means 6 carbons, so that's our N. So 1, 2, 3, 4, 5, 6. And I drew it in the organic chemistry abbreviated way. So again, every point is a carbon. You could also draw it out. 1, 2, 3, 4, 5, 6. And if we draw it out explicitly, right, we have to put a hydrogen and filling it in, so every carbon has 4 bonds. So AKA, again, fully saturated. And then if we count our hydrogens, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that's C6H14, which matches with our formula. So 6 times 2 is 12 plus 2 is 14. And then it doesn't matter if we branch our hexane. So let's see, 1, sure I have 1, 2, 3, 4, 5, 6. So 6 carbons. And then if we draw our hydrogens on there, so 1, 2, 3. Make sure every carbon has 4 bonds. So 1, 2, 3, 4. And so we can count up our hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So right, same formula. It doesn't matter the connectivity as long as it's a alkane, so a acyclic, right? So not a circle. Well, we might as well do the cyclic ones. I usually don't do them now. So a cyclic, I could spell, so our cyclic hydrocarbon, so that follows a slightly different formula, so CnH2n. And so if we take our same 6-membered carbon, and then we put it into a cyclohexane here. So cyclo obviously meaning a circle now. And then you can count them. I didn't draw a very good point there. And so now it's C6, and then H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So C6H12, so slightly different formula pattern. And then, so back to our saturated hydrocarbons, so we can start to get into the naming just a little bit. And so I have our prefixes here, and they kind of follow. And so drawn here is undecane, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 carbons. Of course, we could figure out our formula. So CnH2n plus 2, so C11H24 for our formula. And so then we can just practice drawing. So of course, right, methane, that's for 1 carbon, so we know our methane. Don't forget just our basics, right? It's tetrahedral geometry, sp3 hybridized, so don't forget all those terms. Right under their tetrahedral. And so that's kind of the thing that you want to keep in mind. I got kind of lazy with my molecule. But this is a good time to make use of your molecule kits. Or, right, you can go to Wikipedia. And so the point is in your brain, okay, you're looking at this line here. And you want to think about the geometry. Because, you know, even I did not draw it very well up here. So I just drew a straight chain. But that's not its true geometry, right? Each carbon is a tetrahedral center. And so this is a better representation. You know, again, your molecule kits are a good use for that. So if you want time in lab, you know, again, we can let you into lab so you can play with the MollyMod kits. So you're just kind of thinking, okay, this is its true 3D structure. And just kind of thinking about where our hydrogens are, because everything does kind of matter. And so then just practice writing. So this is just to get us familiar with our small hydrocarbons. So ethane is for 2, and we can even draw it just a line, or, you know, just draw it out. And ethane 2 again, you want to appreciate the 3D structure. Oh, that's too slow. Let me put together ethane, because we should look at the 3D structure. Ah. Somehow I grabbed a carbon with too many holes. And so if you can tell by the way I drew it, I was trying to allude to its most favorable 3D structure. But I'll pass it around. So kind of the key is that you want it to have the most space between all the hydrogen atoms. So it kind of walks, so you just want to look down the carbon, so they're all kind of spaced really far. So as opposed to, right, you could kind of stack them where they're in line with one another. And that's not as favorable. You'll go into it more in like CHEM, but you can just kind of think about, again, most favorably, they want to be far apart. So you can pass that around. So that's how I tried to draw ethane up here, so that's why I put one hydrogen on top. On this side too, kind of on the bottom, trying to show that structure. And so that's also what's shown on Wikipedia. Again, it's showing the most favorable geometry. And I don't want to get too into it, but obviously there's some rotational spectroscopy, so you can kind of tell when it's in the different conformations, but that's getting a little too detailed. I just want you to appreciate that this is, again, the most favorable, or they're really spread apart. And so then we can continue. So propane is 3. So go back to here. Propane, butane, pentane, hexane, heptane, octane, nonane. And of course can go on and on and on past 12. So if you were in the petroleum industry, you might want to know your higher hydrocarbon prefixes, since they would deal with those types of higher boiling. So propane, 1, 2, 3. Draw out your propane. I was trying to give it some 3D structure. So our 3 carbons, so C3, H8. So butane, right, 4. So 1, 2, 3, 4. And so this is, again, straight chain butane. We can draw it out. So it still follows our same formula. And then, so let's look at this one. So what is isobutane? Any thoughts? So an isomer, Carmen, do you have more?
Is it when it's branched instead of linear?
Yes, now we have some branching or isomers. And so then our isobutane, and now this is kind of, you would have to know what an iso group is. So iso tends to be these little branches here. So 1, 2, 3, and then we have our 4 here. So isobutane. And so these all have hydrogen. So it still has the same formula as our butane, right? So it's still C4H10. All right, so that brings us to our structural isomers. And so we kind of said it, but do we have a definition for structural isomers?
Same chemical formula, different molecular arrangement.
Yeah, so same chemical formula, and we can say either different arrangement of atoms. You could also phrase that connectivity. And we've kind of seen that a little bit if we think back to when we were like comparing our polarity and our dipole moments. So we're comparing like ether groups versus alcohol groups, right? And they have different properties. So we mentioned one is hydrogen bonding, one is just polar. So those different isomers give it different properties. And again, same chemical formula. All right, and let's look at some reactions. And so, of course, we know that hydrocarbons undergo combustion reactions. So we could just look at one example. So we can look at the combustion of propane. And of course, right, this hydrocarbon could have had an oxygen here. It just happened to not in this case. And then we always make CO2 and water as our products. And we always assume a complete combustion. So an incomplete combustion, you form CO. And so one other type of reaction, so we won't get into all the reactions, we'll just kind of look at a few. And so one thing that alkanes can do is they can undergo substitution. And so let's look at this. So we have a halogen. So this is generally a halogen. So right, bromine, fluorine could also work, iodine. And then the other key is the UV light. And so this indicates a radical mechanism. And so that's actually how this reaction is initiated, is that you have your chlorines. And then that UV light breaks apart that bond. And so half arrow notation. So we actually form a chlorine radical, so that goes on to react with our methane here. So then we make our chloroform, so it's just our singly substituted methane, and then that would also form HCl with our other radical. And so you see this substitution reaction. Let's see, so other things to kind of recap on. So right, don't forget about your hybridization. And so right, we see all the hybridizations in our carbon. So we can have sp products, such as from CO, sp2, like an acetone. And don't forget what orbitals go in, right? So this is an S and 1p. To combine, our sp is, right, our sp2 is now 2 p's. And then, of course, sp3. Obviously, an S and our 3 p's. All right, so that's just kind of our reminder. And so now let's look at the naming, again, in a little more detail. So our naming starts to get a little complicated, but we'll look through it. So of course we have our prefixes to help us. So now this gives a little higher ones like 20, eco-sun. And then we also want to look at our functional groups. So our functional groups are sometimes just represented by an R. And so then what is that R? And so we have our simplest is a methyl group. So of course, right, methyl, that's important in drugs. Now we're going to go into drug the class. So right, obviously that's why the methyl group with meth, it makes it more potent, right? So if you take amphetamine, methylate it, any sort of methyl group helps it cross that blood-brain barrier. And then fluoro are actually pretty similar to that, so these fluoro groups. So that's why there's a lot of fluorines or even CF3 groups in medicine. So all those help with the blood-brain barrier crossing. Then there's, so of course, right, you can also have different chains coming off your main chain, and those can be different lengths, right? So methyl, ethyl, propyl is a straight chain, and then there's this isopropyl. So isopropyl comes up a lot, and that is just this right here, isopropyl. Just this two branching. Yeah, so this would be, so isopropyl alcohol, so running with that would be isopropyl group with an OH on there for the alcohol. And so then, like we mentioned, we can have fluoro, chloro, bromo, iodo groups on there as well. And then if you have an amine, it's an amino. Nitro groups are also common. They're usually colorful. Could be toxic though, so you got to be careful with those nitro compounds. They're used in like dyes and stuff, but like I said, if they're really highly colored, bright, they tend to be toxic. And then phenyl group, so this is like our aromatic benzene ring. All right, so let's look at these rules and then we'll do some practice here. And so these are kind of, again, our rules for naming, but then we'll put them in practice. And so the first one is the most important and usually the most difficult, shockingly. So you want to find your longest continuous carbon chain. And what's kind of tricky is when you're looking at these organic structures, you know, you kind of draw it in one way to imply a bend, but you want to just find the longest chain. So even if it looks like it's branching, right, because your representation is just kind of a depiction. So you have to find your longest chain. And then the next trick is to identify and name your groups. And then you want to number your chain. And you might have to kind of practice with this, like play with it. And again, you'll see what I mean once we do this. But you have to practice and see, like, is this the proper way to number the chain? So you might want, you'll have to test that. And so you want to start at the end nearest a substituent group. So you usually want to get the lowest numbers. And then you designate the location with its number, and then of course the name. And then we'll actually write the name in alphabetical order, and then ignore your prefixes when alphabetizing. All right. So let me draw up two scenarios here. So see if you can name this compound. Oh no, 1, 2, 3, 4, 5, 6, 7. All right. So what is the name of this compound? And so I'll give you a second to look at it. So see if you can identify the longest chain, right? Find the groups. And then what number might we order them in? Do you have an answer, Carmen? So 2-bromo, 6-chloroheptane. So that looks good, and let's kind of walk through that together so we can see how she got that. And so kind of the first question is, okay, well now that you have this, right, you have two ways to number it. So I'm going to duplicate this structure. And so we could go, right, 1, 2, 3, 4, 5, 6, 7, since this was our longest chain, or 1, 2, 3, 4, 5, 6, 7. But you want to give priority to the largest molecule, so the one with the biggest molecular weight, so that would be bromine. So bromine takes priority, meaning we want to give it the lowest number, and so that's why this is the appropriate answer there. And so, right, and then you just identify, so we have a bromine and a chlorine, so that's bromo, chloro. And so then, right, they're put in alphabetical order, and then they have their numbers to indicate the position on our heptane chain. So let's try a slightly different one and see if we can name it. And so now what is this one? 1, 2, 3, 4, 5, 6, 7. And so let's, again, go through our numbering issue. So we could either number it 1, let me get something brighter. Go pink. So 1, 2, 3, 4, 5, 6, 7. Or we can number it 1, 2, 3, 4, 5, 6, 7. And so what's different in this one than compared to the last one?
There's methyl grouping, the edge closer to chlorine,
Ye-
and the way the counting rules work
exactly.
So we have to swap around the way we're counting from the previous module.
Yeah. So, right, follow along with the logic. So you're kind of comparing, right? We can either make these last two ones 5 and 6, but then you have two of a lower priority as opposed to giving our higher numbers to 2 and then leaving bromine with the 1. Or like how he phrased it, right? If you have a branching, then it takes priority. So then this is our correct counting and numbering. And so what does that give us for a name? Someone want to go for it?
Chloral 3-methyl 6-bromoheptane.
Oh, do you have the right things? But then we still put it in alphabetical order. So 6-bromo, 2-chloro, and then methyl. So 3-methylheptane. So yeah, still go in alphabetical order, and then the numbers just tell its position. Questions about these two examples? All right, so now see if you can try this activity. And so now we want to figure out all the possible names and structural isomers of heptane. And so I gave you the hint that there are 9 unique isomers. So see if you can draw them. So I'll give you a few minutes to try to come up with them. Make sure you don't repeat any. Ask your neighbor, and then we'll start throwing them on the board. All right, who wants to put one on the board? Of course, if you go first, it's probably easier. Okay, go for it. Uh-oh. Is there no markers? Okay, let me go get some markers.
Tub of You can just go with the easiest one first, the straight.
Oh, yeah.
Too boring, yeah. Too easy for Lyra. The schools make it kind of look like they're outside. I know, that's what I was
Yeah.
saying.
One, two, three.
This oxygen background is come.
You like explode.
Very expensive.
Makes more sense in this way.
Okay, so 1, 2, 3, 4, 5. So this is a good one to find your longest chain. So this is what I mean by we draw them all screwy. So I find a 6-carbon chain. So 1, 2, 3, 4, 5, 6, and then it looks like you have a methyl group off of the 1, 2, 3, third one. So 1, 2, 3. So it looks like that. So what would be the name of your compound here?
I haven't gotten that far. Okay, so it'd be 3-methyl.
Heptane or?
Kind of this 1, 2, 3, 4, 5, 6. Oh, 3-methyl hexane.
Yeah, so 3-methyl hexane. So we have one isomer on the board.
One of the other colors, I like calling these chains.
Oh, yeah. Right. One more. Which one?
Because it's like, comes off of it, and then he comes off of it again, so like.
Yeah, this is what I mean by draw.
I drew it weird, yeah.
Yeah, he drew it funky, but just find the longest chain, right? 1, 2, 3, 4, 5, 6. It's really just,
Oh, I get it.
And you guys want that?
yeah. That's like the second hardest part of OChem. It was just like, yeah, drawing it in a way that everybody understands, or like translating your drawings.
So this would be like a better way to draw it.
So who wants to put another isomer? I guess we'll just give heptane. No one wants to do the easy one. 1, 2, 3, 4, 5, 6, 7. Also, biggest tip for OCHEM is count and then count again. Even really smart professors make silly mistakes and like drop carbons. See that online.
Next.
Yeah, throw one up there.
Okay. And let's see. This one doesn't work. Okay, so got 16 on ours for ours, right? It's like
Yeah.
seven carbons. Okay. So then I've got my longest chain right here, which is 1, 2, 3, 4, 5. So that's going to be a pentane, correct?
Yep.
So pentane have two methyl groups, one on the second carbon and another on the third carbon. So that would be 2, 3 methyl pentane.
So 2, 3. And then in this case, we can use a di to indicate that there are two methyl groups. So
okay.
dimethylpentane.
Gotcha.
So that looks good. All right, who wants to go next?
I'll go.
So we have 3 out of the 9, so still pretty good at odds. Oh, let's stay away from circles, though.
What? That counts though. That's the formula.
It has a formula, really?
Yeah, doesn't it?
I think it'd be
Oh,
odd.
it has less hydrogens, doesn't it?
Yeah.
Sad. My fun one doesn't work. Okay, I'll do a boring one.
Can't do boring one. Boring one's already taken.
Isn't that one different?
Yeah.
Yeah.
Different position. So now what we've done is essentially move this methyl group to that carbon. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so it's, oh, you put the name, perfect. So 2-methylhexane. So I think we have all the hexane isomers. So that's a hint. Who wants to try another one? Are you going for it? Sweet.
We can also, like this one, just have another pentane. Put our methyl groups here.
Yeah.
This would be 2, 4.
So 2, 4 dimethylpentane. There might be other pentane permutations. What else could we do?
Could we stack the two?
You mean like put them on the same carbon? Yeah, so we can do that. So which way do you want to do it first? Because we could put them on the 2 position or the 3.
Let's do it in the middle.
So we can do the middle. So we actually have to draw them all, but we'll start with this one. So this one looks funky. But that is, so 3,3 dimethylpentane.
You can't just say 3 dimethylpentane.
No, because you got to indicate, I know, it seems redundant, but you're trying to indicate, because right, each thing is telling you different pieces, because the di is just telling you, okay, well, you have 2 methyl groups, but then you need both numbers to tell you each position, yeah. So it's not just implied. So even though it looks funny, because you could have something like 222 or whatever, or 333, yeah, like it gets weird, but it's fine. Where else could, so you said stack them, so we could stack them on the 2, right? So we could have 2 methyl groups on the 2. Yeah, so now we have 2,2 dimethyl pentane. Let's see. How many do we have? 1, 2, 3, 4, 5, 6, 7. So now we're missing just 2, and they are kind of tricky ones. What else could we do? You could start with the pentane. What's up? So what'd you say? So let's try that though. So 1, 2. So I think the problem is this is actually a longer chain somewhere else. So 1. Do you want to draw it? I feel like it's probably a duplicate structure. Well, we'll see. Here, let me erase this. So 1, 2, 3, 4. So then that gives us 1, 2, 3. Yeah, that works. Okay. But it's not, hang on, I'm confused. Yeah, see, it's 2 methyls, so not an ethyl. But that works. Oops.
I see. I did that wrong.
Yeah, but it's, your structure's correct.
Two methyl and not, okay,
Yeah, wait, so what's the name of this?
So 2,2 di.
But then you have a 3. Yeah, 2,2,3 trimethyl. I know, that one was a weird one. So trimethyl butane. And so that one is also kind of weird because you could count it right 1, 2, 3, 4, and that would still give you 2,2,3 trimethyl, or 1, 2, 3, 4, still 2,2,3 trimethyl.
So with the last one, just be flipping those? Flipping it. Oh, I guess it's the same structure.
Yeah.
Because then you just count it to the other side. Yeah, that'd be the same.
But there's another permutation, because I actually thought she had the permutation I'm thinking of. Because there's something you could do with the pentane. And you have, yeah, we did 3, 3. what else could you do with these two carbons? You have them all separated in every permutation.
Could you have like an ethyl group in the middle?
Yeah, so that is the last permutation. So the ethyl group has to be in the middle, or else it adds to the longest chain. And so 1, 2, 3, 4, 5, and then so 3 ethyl pentane is our last one. Yeah, that's about right. All right, I guess we might as well stop 5 minutes early. So we'll just continue on. So we'll look at more isomers, get at least a taste of the alkenes and the alkynes, and then look at a few more reactions. And then we'll have our quiz over last week's material, which now I can't even remember what we did last week. Oh yeah, electrochemistry, redox potentials, so all that good stuff. Oh, these are. No, you can hang on to it.
Also, my
Oh, are we?
okay.
I just didn't want to mix it in with the graded.
Yeah.
Actually, no, I think.